Okay. So how was the homework? Did you guys enjoy it? Enjoy building shell? Extensions are easy, right? But what was the challenge? I've seen so many people struggling with building this recursion into pipes. It's not even like part of the operating systems, right? It's just recursion. At least people who wanted to, who came talk to me during the office hours. But anyway, so now you kind of know what shell provides and how it's built to a degree to which you were able to understand it, but it's reasonable. It would be kind of fun in modern world to try to use modern AI. So did anyone use AI models to build the shell? Not yet. So try it. I don't know. I didn't try myself, but maybe it will come pretty close. Apparently, they're very powerful these days. Okay, so we extended the quiz deadline until Friday, and it was done late night. So I apologize for that. But people who haven't done it can do it until Friday. And I think we're ready with the next homework, which asks you to load a simple ELF binary. So the main part just says load, so essentially just the header of the ELF file and a loop through the program header table, and the extra credit part will ask you to relocate the binary. So the main part is relatively easy, easier than shell, I would say. But again, kind of a little bit involved, so start early. So today our plan is to finish, I'll just quickly finish explaining how Linux loads, or how real operating system load executable programs in memory, and then we will start a new subject, which is address translation. And that's the last thing which is between us and booting on the real hardware, just because unless you know how address translation works, you can't really boot. Okay, so we were talking before about static and dynamic libraries, and let's take a look at how those things are loaded in memory, right? So first of all, we already discussed it, right? So we said, okay, we knew that, okay, if you have an ELF container and you have a statically linked program, then it's more or less ready to run. So what do you think is still missing? What step the operating system needs to do? Sometimes, not always, but often. Like, what do you have in a program? You have an ELF header. You have this wonderful program section header, which points you to other parts of the program, which are, roughly speaking, executable. Something like maybe goes here, and this part is read-only, and so on, right? So loading seems to be relatively easy. So the operating system just looks at the header, finds out where this program header table is located in the ELF file, and then it does what? No, anyone? Correct, and this is your homework. So essentially, in a loop, you will say, okay, I look at this section, and maybe it's like read-only and executable, so you will configure the page table or the segment or both, depending on what hardware you're running, and essentially say, look, this region of memory will be for you, and you just load it from disk, right? And loading from disk is literally just reading a file and writing in memory, right? So not super hard. Agree? what's next? So you go one by one. So read only. This is like maybe a data section. This is like maybe init section, which runs before main. Maybe this is a text section of a program. Maybe, I don't know what else can be read only, but okay, there will be BSS section or like writable data here. So are we ready to go at this point? So imagine we loaded everything in memory, right? So this is memory. This is disk. I just wanted to make sure that you understand that what is involved. No? Yes, no? Who says yes? No one wants to say yes. You can guess by how I say it, right? Okay, who says no? Everyone else no? Like, okay, everyone is undecided. No, remember the thing is that every time you have something like a move instruction which touches a data section, there will be a real address here, A, right? And if it happens that, imagine this address, sorry, which you are trying to access, if this is address A, which means that you linked your program to run at a specific address, let's say maybe address 0, or maybe it's address 1 megabyte, then you can just simply load and go forward, right? So everything will be just fine. If, however, operating system says, okay, look, I see that the linker linked the program to run at address 0, remember that this will contain the virtual memory addresses of the sections, right? And if it doesn't match and you say, look, by the way, I really prefer address 0 is so special that I don't want to use it because, you know, attackers are using it, you do null pointer dereference, you immediately land on this source instruction. So like, it's a little, it really happened in the past. So, but imagine you say like, okay, let's not use 0, use whatever, some other address. Then you have to relocate, right? So essentially you do this step and then you will have a relocation table here as well. And like, it has a slightly more involved organization than just one layer, but essentially it tells you, okay, that this address has to be like relocated. And if you shift it by x1000, then you know it will be A plus x100000, right? Agree with this? And then you're ready to run. So this is for static programs because everything is already linked together. All your libcs are sitting here in this section, or your main is sitting here as well, right? Agree? Good. Okay, I just wanted to understand that to make sure that we understand that this is it. So essentially, when you say it, and this is how x86 will be running programs, right? x86 is very simple. It will not even be relocating programs. Everything will be linked to run at address 0, loaded at address 0, and you just essentially get the entry point from the ELF header and whatever it is. Typically, it's start running, right? Okay, so, and this is exactly what my slide is saying. So remember, we execute programs with the exec system call, right? So exec-v in this example. So the kernel reads program from disk. It can handle multiple executable formats. And this is another wrinkle here, which is kind of interesting. So it tries them all. So it tries, for example, ELF and say, okay, it's ELF. I'm going to load and run it. Maybe it can load AOut. Remember, we talked about AOut as a like format which was used in the past. But it also can execute like shell scripts, right, or scripts in different languages. So for example, if the program starts with the symbol, and maybe it's a Perl or a shell script, it will execute the interpreter instead. So it will understand it, right? And instead of linking and loading, it will link load interpreter or load interpreter, and then just pass this as an argument. We'll, for a second, concentrate on ELF just because it's our main subject. But I just wanted to make sure that we understand this part as well, because like it's not that I'm running a lot of shell scripts, but I might run some. What is that? Where do we have shell scripts these days? I don't even know anymore. Okay, maybe let's skip. I just wanted to Does anyone know allocation of any simple shell script? User bin, permission denied. Man, let's start from user bin. For example, something like this, right? So user bin NVIDIA sleep, for example, whatever, who knows what NVIDIA is doing. Oops. But essentially, kernel can understand that this asks for the interpreter, and this is the interpreter itself, right? So it's kind of like a bit of knowledge, which is somewhat useful, right? Okay. But remember, I was telling you that a lot of things, or potentially a fair fraction of things, can be running before main, right? So your main is actually here, right? And if this is your start entry point, right, you first will execute all of it, and only then jump to main. And there is a lot going on, and I don't want to like talk about all of it, but I just wanted to make sure that your main, like the first line of main, is not the first thing which is executing when you loaded the program. So it's wrapped in those layers of libc. And if you want to see what's running in like before main, you can use this. So inside GDB, you can set backtrace past main on. And if you, like from our first homework, if we breakpoint on main, like you start. I think that was the first line of main, and you say, show me the backtrace. After setting this past main on, it will show you that, okay, you started from a start symbol, then executed libc start main, and then you're inside main. And it doesn't capture the history, it captures the call for like the call chain, right? Because a lot of other things were running, but just exited, returned, right? And you can alternatively, if you're real like hands-on kernel hacker, you say, look, I will read the ELF file with a readelf tool. I will take a look at the entry point, and you say, look, this is where the entry point will be. So it's not address 0, it's this address. And you say, look, I will just set a breakpoint on this address, and then you can single step like immediately when the program starts running. That's the alternative. Like if you want to really like single step through everything. So, but a real like example of what can be running there is this initializers and finalizers. So essentially, I was mentioning that before, that C++ needs an execution context to execute static constructors, right? Because arguably that's not the best feature in a language, that you execute constructors, because allow execution in static constructors, not just plain say, okay, those are either zeros, or you use some kind of a macro which executes the compile time and says, okay, maybe it's 0, 1, 0, 1, 0, 1. But you say, look, this is a constructor. So what's wrong with this? What goes wrong? Why do you think? Do you have any idea? What's wrong with static constructors from the standpoint of a language design?
They're probably single-threaded.
They are probably, that's correct, they're single-threaded. So there is a performance issue. So if you really want to initialize something bulky and do that with multiple threads, you're kind of doomed. But I think in a constructor, you can very well start a thread, because it's executing. All the APIs are already running. So you can actually create a thread and go from it. Yeah, so I take it back. It's not single-threaded. You had an idea?
Would you run into some issue where static needs to be shared across everything, not everything, but the whole program needs to be aware of this with that? So languages are like total loss of language.
No, this is already, all the runtime environment is ready for you. Linker did it. I think if I understand correctly, and I'm not a language designer, but just like the real problem is dependencies. So essentially, if you reorder them, if the runtime doesn't know really the order, and something depends on something already being initialized, you might get lucky or unlucky. If you're unlucky, then you're kind of exit at this point. You also might have something like cyclic dependencies, but probably that you can like, that's a problem anywhere, right? But that's essentially maybe not a good design choice, right? So here it is, order of execution matters, right? And ideally, the language should track dependencies or whatever your mechanism which allows you to declare those static constructors should track them. But this is not done. So they just simply say that the system libraries go first in the init section, and the user then will go in this CTOR section. I don't know what it stands for. Constructor, yeah, good guess, thank you. And in C, like if you don't like C++, but just want to code something in C, this is the attribute which CCC understands. So essentially, this function will be executed before main. So if it does a printf here, you will see constructor and then main, right? So it does your runtime, like this thing registers itself in a table, for example, and the libc initialization environment will just invoke this function, say, okay, it's needed for the program to run, so I will invoke it, right? Similar for the finalizers, and so they will be running somewhere, right? So like global constructors, something. So this is from a blog post. I don't want to go too deep into the details. I never bothered to understand myself, but I was curious about what's going on before main, right? And there is a blog post which I cite from the end of the slide deck, which you can go ahead and look in details. Okay, that was about static programs, but dynamic programs are kind of funkier, right? So what is going on with dynamic programs? Again, imagine you link dynamically. You have your elf here. You have your main. Like you have your, obviously, like I'll skip some details, but I will emphasize something else. So this is your, let's say, text section of this thing. This is your main, and this is your data section. So what do we do to load this? What's the difference between statically linked and dynamically linked programs? At least this we have to understand by the end of this class. There can be a global offset table. I mean, the way I taught it, I said that position-independent code is almost always used in dynamically linked programs. And what's the reason for that? Why are we using position-independent code?
Because it might be shared between multiple programs. That page would be loaded in different addresses in different programs, and then it's the same exact binary.
Correct. So we wanted to make sure that we avoid the conflict. When we load libc, it might be at address A in one binary and at address B in another binary, right? So and then position-independent code can allow us to say, look, just do that in virtual memory. We still didn't cover virtual memory. We'll cover it later today or next week. But then you can share region of physical memory, which says, okay, this is your binary. It can stay the same, right? But I was kind of in passing mentioning that, okay, this is kind of an advanced technique. So people didn't invent it right away. So they first were using dynamically loaded libraries. So Windows was specifically doing it. And just said, okay, well, whatever. Every process will load libc at this address. If you cannot, then you're unlucky and the sharing for you disappears. So we will pay the price. So they were not using position-independent code. And on Linux, you can do the same. So you can, I think you can play tricks and say, okay, compile everything without position-independent code. And I mean, why it matters? I mean, I told you that it's some additional overhead. You go through the global offset table, one additional memory reference. You go through PLT to dynamically resolve functions which are not linked, right? So it's some additional overhead as well. You can argue that most likely you can structure your program that it's not happening anyway, because you will inline everything what matters, you know, with like your tight loop, which really reads the packets from the network and goes to the whatever Apache execution engine, which you have to spit like billions of pages a second, will be optimized and will not use global variables, for example. But maybe you will use one or two. Maybe it doesn't matter, right? So it's a questionable argument. So, but nevertheless, right? So you have to understand that it's possible. But again, in terms of loading, so what do we have to do? Because where is our libc to begin with? Where is printf? So printf is sitting somewhere in another L file, right? Imagine this is your libc library. Let's imagine printf. It also has a data section. As you say, it will have this GOT as well, right? And you will have GOT as well, and PLT and whatnot, right? So then it's a little magical. We say, look, this is your executable main, and this is your libc SO. They're sitting on disk. We somehow have to do everything. So who does it? What part of the system does it? Does the linking? Because it's clearly not connected yet. Because if you had a call from a printf, it's still like OX, FF, whatever. Right? It's unresolved. No, like it goes to the POT and simplified here a little bit, right? So, but if it, because it's all position independent code at this point. So what do you think needs to happen to load a dynamically linked binary?
The loader that loads the library as well as the program.
Correct. So then operating system will be a little bit more sophisticated, right? And there's a couple of approaches. You can build everything. Remember, I used to draw this yellow part at the bottom, which I call kernel. This is the privileged part of the operating system kernel, which really implements exec, and it can do everything in memory. So it can, you know, like load everything, do everything in the kernel. Do the main, do the data section, do the data, load printf somewhere, load printf's data section, make sure that, you know, GOT of this one correctly points to printf, or like whatever, through PLT, obviously, right? So everything is like connected in memory. Agree? So it's a little bit more involved. However, this is not how it's done. What's done instead is that operating system kernel, at least on Linux, loads a special linker in the address space of a process first. It said, okay, instead of building it in a kernel, I will actually build it here. Why is that, you think? And there might be multiple reasons, and to be honest, I don't know them for real, but my guess is that one big reason is, well, first of all, you have a freedom of developing different linkers. You can update them, you know, at user level, the kernel can stay the same, right? But one of the most important reasons today, arguably, is the fact that, you know, it's kind of not so hard to find a vulnerability in a linker, because it's a complex piece of machinery, parses a ton of data structures, you know, like, well, exploitable, right? So if you find an exploit in a kernel somewhere over here, then you own this machine. If you find an exploit here in a linker because you pass some obscure argument, your GOT is like somehow misformatted, and the linker says, okay, I will start reading memory at address 0, then your process goes away, but at least your system is still yours, right? So that's the argument of pushing stuff outside of the kernel. So it became kind of popular these days, bit by bit. Of course, we still get stuck with legacy systems like Linux and Windows, which have a full-featured kernel. But, you know, like if you look at hypervisors, then they implement almost nothing that, in, let's say, rank -1, but push everything to the user level for security purposes. And we can talk about it a little bit later in the class. Yeah.
Shared libraries have different data sections from
Do shared libraries have different data sections for what?
for every different program.
Yeah, because it's your private. Because if you have a variable A, then you have to load this thing, and this is yours. The argument is that this text section is way larger than the data section because you have a smaller number of. You have the private GOT, private PLT. No, I don't know, maybe PLT can be shared, right? So private GOT, private data. Read-only data can be shared, I guess, right? So I know because it's read-only, that's why, right? And if you map it as read-only. Agree? So most likely. Any questions about it? So let me just go through this. When I was a student, I was kind of, you know, it was a surprise. I didn't know how it works. And only many years later, I figured out, okay, and I mean, I was building kernels, but I never bothered, you know, to load dynamically linked libraries, so because it's so hard that you never get to it anyway. So it essentially figures out that there is a specific flag, this PT interpreter in the ELF header, And what it does is it reads the file name of the interpreter and loads the interpreter, or the kernel loads the interpreter in the program's memory, and just essentially passes control to this interpreter. And the interpreter itself, I mean, the way it uses those pass variables right from the environment, which is like a defined way to figure out where to search for the interpreter in a file system, right? And it doesn't matter much, so those are just like low-level details. But essentially, this interpreter like loads libraries one by one in memory, resolving all dependencies, right? I don't know if we compile something like, you know, let's go to the example of bin. What do we have cat here? I think how do we, oh man, how do we read the dependencies of a binary? Do we know? Unix. LDD, sorry. So it essentially tells us that, okay, libc depends located here. So essentially here it's only libc and this Linux VSD, so I think it's a linker itself. Or maybe I'm wrong, but doesn't matter. But essentially this is the way. So if you search for something LDD ZNU, for example, not a dynamically linked library, so this is static, zgif, also static. Anyway, but you got the point. So you load something first that first figures out the dependency, loads everything. If it fails at this point, it says, okay, I cannot load because you don't have a library which you need to run. And I have a record, like I know that you need it because you mentioned it. That's essentially what's going on. So you initialize the pieces which you need to run the position-independent code, this GOT specifically, right? And that's it. So that's probably what I wanted to explain. I just wanted to double check the path of the interpreter. I don't have it on the slide, so I don't remember. Okay, so that's it. So we're done with the links which I used to develop those lectures. The best way to understand what's going on is to essentially quickly read through those links, and I assign them. You don't have to go very deep, but you need to understand at least high-level picture, and then your homework will ask you to understand the low-level picture, right? So which is learning by doing. So we're done with relocation. So kind of next time we'll see if we'll be looking at exec and implementation of the exec system call in the x86 kernel. Any questions about linking and loading, on which we spent like 2.5 at least lectures? All good? Everyone is tired of linking and loading? Me too. Typically, you know, you get tired by the end of it, but it comes back useful often. Okay, so let's switch then. Our next topic is this wonderful address translation. Again, we talked about general registers, right? And they're fine, but clearly they allow you to execute only one program at a time, right? And we kind of, I mentioned it in the introduction, that the operating system kernel, that yellow piece, can switch from one process to another by saving the registers and apparently restoring it from a previously saved registers. So you can context switch between programs, right? But we also had this idea that we want to run multiple programs in one memory, right? So maybe we don't even have a preemptive multitasking. We're just using a yield system call to donate our time slice to the next program, right? But if I ask you, if you want to build this, how can you implement this in user? You somehow need to share memory between multiple programs. Or if you want a different term, I can say you want to virtualize memory, meaning that you have one physical memory, but you want the programs to believe that each program has its own private copy. So how would you do this? Any guesses? Like, did anyone take like any embedded system class? Okay, tell me. So did you like embedded systems don't even have page tables often. So what was happening there? Do you remember? How do they run?
On the embedded system, normally don't have OS.
They do actually, almost like embedded systems do have OS. You'll be surprised. Okay, but maybe what I was trying to hint is that like you can first think, okay, I have this wonderful relocation mechanism, right? So why don't I just relocate multiple instances of the same program or different programs to run at different addresses, right? So why not? Then something like that can happen, right? You say, that's my memory. One of the programs, maybe it's the same LS, instance 1 and instance 2 here. One is relocated to run at address 0. One is relocated to run at this address, right? So there is a tiny gap between them. And you can very well do that. You know that this is clearly possible. I just taught you how to relocate stuff, right? So you will have your text section here, text section here, private instance of data here, heap, and a private stack, right? And if you have an instance of a variable x here, one will be here, another will be here, right? So clearly it's possible, right? What can go wrong with this approach, or what is not ideal?
Each process can get at the other process.
Yeah, you say, look, protection is missing, right? So you know if you like accidentally have a stray load or store instruction, you suddenly like reach out here, right? And you say, well, can it be fixed or not? Who can tell me how can it be fixed? Did you ever play? Yeah, go ahead.
Can the operating system keep track of which like memory it's supposed to be in, and if it's outside of that range?
Yeah, but what is your mechanism to store a seg fault? Literally here you have a move instruction which loads something in the EAX register from, I don't know, address which is inside EBX register. How can you stop this move? Because you say, I want to throw a seg fault, but really to throw a seg fault, you have to detect that there is a violation.
Well, then you need to tell the CPU that, hey, their addresses this process can go into. And in order to do that, you have to have different levels of execution privilege.
That's one way to do this. So what you're arguing for, and we will get to that shortly, you say, look, I will ask for hardware support. And my easiest hardware support saying that maybe there is a notion of a segment. And it has a beginning and the end. And the hardware just checks the bounds of the segment on every move instruction. But I was first curious. I was just, and this is how people typically explain it, but I wanted to make sure that we understand that we can enforce these limits in software. We can build segments in software. So the question is how. And I mean, all of you ran them. That's ironic. So this technology is used today. Like, for example, did you ever play like Quake inside the web browser? Or that was, I mean, maybe no one plays Quake anymore. It was me.
We can just not run code directly.
We can interpret, which this is a great idea. I didn't think about it. But what you can say is that instead of running, you will literally just run a software, piece of software which you built, which emulates the CPU in software. Do we understand how to do that? So just like it's a for loop which says I will fetch, decode every instruction. We'll have some data structure which represents registers, and we'll do that over and over and over, right? What's wrong with this? Although it's done in practice as well. So what's the obvious disadvantage? It's relatively slow, but you will be surprised how fast it can be made. I will come back to it later when we reach virtualization. It intuitively like you read an instruction from memory. CPU does it in one cycle, but here you have to decode the instruction, saying, okay, what is it a move or is it a jump? And you execute a range of instructions, maybe 20, maybe 50. So it's like 50 times slower, unless you do advanced optimization techniques, which we'll discuss later briefly. But interpretation is one option, right? Why not? If you're smart about it, you can optimize, and I will show. It's actually like, again, it blows your mind how much you can optimize. Let me show you. I don't know, since we're on it. Linux in a browser. Oh, this one. Which one would we like? x86? Let's try. We spent some time loading it, but you'll see it's fairly fast. Oh, booted, maybe faster than your real hardware. CD. I mean, it looks like nothing. It looks like, okay, the guy just showed us another black screen. What happens underneath? There's a interpreter of x86 hardware implemented in JavaScript, which runs inside your web browser or inside my web browser. And it faithfully emulates Linux hardware. So, and I mean, like to a human, I mean, you will run the benchmarks. It's obviously slower, but at least it booted in like, in seconds, which is amazing, right? So it's doable. And I'll explain how later. But let's get back to this. So how else? How can we enforce bounds in software, sorry. I just wanted to, it's important today because it became part of the security story and we'll see more and more of it. Yeah.
So on the screen, are those the physical addresses?
Is what?
Are you representing physical addresses on the screen?
Let's imagine, yeah, physical addresses.
So why can't you just use like virtual addresses?
No, but for that you need hardware support, which like my segment here is one way to virtualize memory by asking hardware to do this. I will explain how it works in a second. But I wanted you to understand that it's a move instruction. What we literally want to enforce is to check that this address, EBX, is in bounds between S and start and end. So literally speaking, you can take your compiler and say, in front of every move instruction, put a check, kind of like if it's EBX is greater than S and EBX is less than end, right? And it's called a binary rewriting. So essentially, I take a binary, I take a compiler, or I do a disassembly, or better to do that at the level of a compiler. I understand where my compiler will emit a move instruction, and I will insert the bound checks. And arguably, I can do that if I do a specific layout of a header space. I can, instead of doing the check, I can just really mask the address, saying that addresses from 1 gigabyte, from 0 to 1 gigabyte is one process, 1 to 2 gigabyte is another process, and I will just mask the upper addresses, essentially just saying you always run with 2, for example, here, right? So it's one instruction overhead. So I don't know if you were familiar with this technology. So it's something like Google NACL was one of the, like in general, it's called software fault isolation. So those techniques, like where you say, look, I will enforce those bounds in software through binary rewriting, were known forever. Google NACL was a very fast implementation, which achieves like 10% overhead, which is blazingly fast, with some additional restrictions. But today it evolved into something like WebAssembly, WASM. So you probably heard of it, right? So WebAssembly is a slightly different take on a similar software fault isolation technique, right? Again, just wanted to make sure that, okay, it can be done in software. But as you say, as you were suggesting, another way to do is to virtualize memory, or another way, ask for hardware support. So kind of similar idea. And this is how it started. So essentially, early CPUs were providing this abstraction of segments or segmentation. It's very easy, so very simple. So we're aiming for the illusion of a private address space. So essentially, each program will have its own private address 0, right? It's just easier. If you already linked it to run at 0, you don't have to relocate it. You just load it and configure a segment, and each program will have its own zero. So how it's done? It's done in the following way. So the operating system configures a couple of registers which hold these values. Base of a first segment, which means that if you're trying to access address 0, the hardware underneath adds 0 plus base, and you are accessing this physical address. You also will have a limit or a size of a segment saying, and hardware will check if you're trying to access anything outside of it. So you cannot access anything here, right? So for any address X, the hardware will say, okay, what's your current base? I will add it to X, and this is where you will land in physical memory. So it's very similar to what I was just trying to advertise just a second ago. If a second program has the same address X, the operating system will configure a different base. This different base will be added to X, and it will be landed here in physical memory. This is the idea of segmentation, right? So multiple embedded CPUs implement this idea, and x86 before version 386, right? Oh man, probably you don't even know those versions. It's before Pentium, essentially. I think this is the first version, 386 of the Intel CPU, in which page tables showed up. So before that, that was all segmentation, right? But this is the segmentation idea. Why am I teaching it? Because it's still there. It kind of started dying out, so Intel dropped parts away, but it's still there. So if you want a boot operating system, you still have to think about segments. I mean, if we were not booting it, I would probably just skip it and just move forward to page tables, right? Okay, but let's take a look at this at the segmentation for a second, right? So clearly, we achieved what we wanted, right? So we have, like, we can share memory between multiple programs, right? So if I will ask you, okay, like before I build my dramatic story, like I just wanted to make sure that where does this base address come from? It comes from hardware. So essentially, hardware can maintain a table of base addresses, and the operating system can switch between them. And it caches this value in a specific register, so it's actually very fast. So in one cycle. So this is how this table looks like. So the operating system says, okay, there will be somewhere this table in memory, and I will configure it to have different bases, right, for different processes or for different parts of a process, right? And there will be a selector register, like a weird name, but it's essentially index into the table, which tells you what is the current base and limit are. So which entry you're using from the table, right? So that's how it's implemented, and we'll again like look at details how x86 does it. So, and I have a more like really okay, sure. Like, I didn't know that I spent that much time on segmentation, but okay, let's go through it slowly. So, I just wanted to make sure that how does it work underneath, to make sure that you understand how it works underneath. So, imagine you have a piece of assembly which moves the value from memory, which is pointed by the register EBX. So I'm using the GNU syntax or AT&T syntax here, AT and T, right? So it goes this way. And for now, EAX contains 0, EBX contains this address, right? So it's equivalent to Intel move EAX from EBX, right? So what happens underneath is that, what am I trying to show here though? So there is a special, as I was saying, the special segment selector. So for example, data segment selector is equal to 1. So it's an index 1 into the table, right? So effectively what the hardware is doing, it will have this table and this segment registers, which Intel provides like for code, stack, data, and a couple of other segments which compiler and the operating systems can use on their own discretion. Essentially, DS equals to 1, right? So this 1 goes into this table. It starts from 0. Entry 0 is not used, but this is where it gets the base, right? This is exactly what I was trying to explain a second ago. It will take the base and the limit here, right? So essentially, if you're running your EBXS X300010, this address, right? The hardware will add this limit to this value. Not the limit. Add the base to this limit, and the physical address to which this load will actually access will be this 410010, right? Because it's a sum of these two. Agree with this? Is that clear? And this is done in hardware, so your instructions don't change. So you still have the CPU itself will use this opcode for this instruction. If you disassemble the program, you will just see this instruction. It's just that the operating system and maybe parts of your runtime will set this DS, will set DS to 1, or rather, we'll configure this table. We'll put it somewhere here in memory. We'll set DS to 1 for one program. And maybe it will be using a different table for another program in such a manner that the address spaces do not overlap between the programs.
Won't this give you problems with, like, your program not being able to grow after it's allocated memory, not being able to grow?
Exactly. And so this is what I'm trying. I was actually thinking that I'm getting, with my dramatic story, I was trying to get to this. But I was just first trying to explain this example. So this is segmentation. This is like to a degree, and you will see more of it, but this is how it's running on Intel, right? It is always on as long as you switch from a real mode. I think it's called protected mode. So essentially, it's impossible on Intel. It's impossible to enable page tables without first enabling segmentation. That's why it's important. You can say, okay, I don't really want to bother with segments, and I will be just using one entry which sets the base to 0 and the limit to max, like 4 GB. And then it's almost like no segments at all. Hardware does it underneath, but all the checks are really passing, right? Because you cover the entire physical memory or entire address space, right? Okay. And each entry in the table will contain the base and the limit, as I was saying. Limit is the size, and some additional access flags, kind of like which privilege level will be able to access this segment. 0, 1 to 3. We'll talk about privilege levels later. And of course, for the hardware to know where this table is located in memory, it will maintain another register. So it's, for example, global descriptor table register, or GDTR, right? And it's literally a pointer to the table in memory, right? So when operating system starts a process and says, okay, you will be using this table, it will configure this value, saying that this is where the segments will be located for this specific program, right? Okay, and if you say, look, maybe just have more slides on how it works. So base comes from the table. So the index comes from the segment register. So this is index 1. Base comes from the table. Address comes from the register itself, like it used before, right? But we do the addition and essentially land on this address, right? So not surprising. The name for this address, which Intel gave it, is called linear. It's a little unusual, but you will see that like later on we will cover it. But that's essentially the name. And if you switch between processes, essentially you will have another table, yellow, somewhere in memory. The operating system will switch the value of this GDTR register. Now it points to this address. Essentially, maybe it's the same. We don't know. The program might be using the same segment register to select the entry in the table. Let's say it's the same one. Now it will have a different base, and this different base lands us somewhere over here. Again, same logic. We add all addresses with the base to essentially do this shift, as I was explaining before, right? So again, kind of clear probably at this point, because nothing is really happening, just a table, right? So this is how, if you look at Intel documents, and I mean, maybe later in this class you will have to force yourself to read through the Intel documentation manuals, right? So, and they are a little bit obscure, but this is how they show it. So essentially they say like the addresses which machine is using are called logical addresses, right? So logical addresses consist of two parts, right? The stuff which was in the register. So like when we do this move instruction and say load something in the EAX from the EBX register, we say that this value is called an offset, and it can be 32 bits. And there is also a segment selector, which is 16 bits, right? So it's yet another of this DS, CS, SS, right? They have names. We didn't cover them before because it didn't matter, because we didn't talk about address translation, right? So we take a selector and it becomes an entry into the, like, selects an entry in the descriptor table, right? This entry itself will contain something what is called a segment descriptor, which will contain base and a limit, right? And specifically, we care, in this example, we care about the base. We take the offset, add it with the base, and we get something what is called a linear address. If you don't have page tables, this linear address goes immediately to your physical memory. So essentially, it goes in a memory bus, and this is the address which the hardware will be using to access physical memory, right? If there is a page tables enabled, this linear address becomes an input to the paging translation, right? And then you will translate linear to physical, and I will cover it a little later, right? But this is essentially the diagram for how segmentation works, right? So it's the same as the previous slide. It's just that this part is from the Intel manual. So if you see this diagram, you say, okay, cool, yeah, I got it. So it's the same what we discussed, just drawn differently, right? Any questions about this? Good. Yeah. So those elements, like I was saying, so have a base address. Logically, they represent these three things. So essentially, base, limit, and access rights. Physically, they are like for historical reasons, they are spread all over the place in this register, but it doesn't matter. You will learn how to read those parts one by one, right? So effectively, if you think about your address which you get here, the formula for the translation looks like this. So it's your offset, which they also called an effective address, plus the entry which you get from the descriptor table, and you use the base field, right? So if you want to think about it this way, that's another way to write it, right? Okay. So let me ask you a question. So we talked about those selectors, right? So I keep mentioning that there is now yet another register, at least one or a couple selectors, which choose entries from this table, right? The question is that where do you think they are? Because I claim that segmentation is always enabled. I disassembled some code in this class. We've never seen a segment register yet. So how does it work? What do you think? I actually think we saw it once, but I quickly moved forward. So how does it work? Like we never seen like anything related to segmentation. I kind of claim, I'm willing to bet that you, even if you heard about segmentation, you never really like seen a segment register in your life. I mean, like, let me ask it differently. Who saw a segment register or did something with a segment register or knows why it's used in the code which you're running?
I don't know if I can answer the last question. But, I wrote a lot of assembly language back in the 286 and 286 days, in which case you had to, the registers didn't were selectors, they were just offset additions.
Yeah. So yeah, okay. So I'm not the most mature person in this class, right? So as I mentioned, page tables appeared only in 386, right? 286 and 8086 only segmentation. It's a hell. I don't know how it was working. I never really programmed it, right? So it's bad. You know more than I do. I think it's a flashback. You think, man, like really, I came here just to hear it again. But other students in the class, does anyone ever use? Did anyone ever use a segment or any segment register? They are actually used in modern systems. Did you ever bother how the thread local variables are implemented? Thread local variables? Variables local to a thread. There is a keyword in C++, thread local, right? Every time you create a thread, you get a private instance. A thread gets a private instance of this variable. How do you think it works? Under the hood, for every thread, they create a specific section. You have a thread, you will use a GS segment to point with you configure it with a specific base, and T1 will have its X variable here. You start another thread, T2, the runtime will create another, it's like thread local section, and GS will be pointing now here. That's why you can have multiple threads, multiple instances of those variables, right? And they are very fast because they are resolved through GS, for example, or FS, one of those segments. We'll come back to it like later, but okay, got it. Okay, let me explain how it runs. So typically those segments are associated with one of three types of storage, like code, data, and stack, right? And so essentially, if you were saying, let's make them explicit, all your programs would have to use an explicit value of those segments, right? So essentially, if it's in a data section, because it's a static variable, right? You would say, okay, DS, go access this address through a DS segment, right? And maybe you have multiple of those because maybe you want to grow your program and you say, look, I dynamically allocate more segments, right? So this hell existed. If this int y is on a stack, then you would use SS here, right? And your code would be like, okay, I want to access X, use DS. I want to access Y, use SS. You want to call a function, use a code segment in front of an address, right? But you say, okay, like it's kind of like very, very verbose and very, very like kind of explicit. You say, like, I know that if the variable is in a data section, just this, let's imply this segment, right? And this is what CPU essentially is doing. For a code, like control flow instructions, they imply that they say, okay, let's just use the code segment. And if the programmer wants to overwrite and say, like I was saying, like maybe it's a thread local variable. Let's say, I don't know what the syntax is in C, but let's say thread local. And you say it's int Z. And then what it means is that really the compiler will be saying GSZ, or maybe depending on implementation, FSZ, right? Meaning that it will actually put a segment in front of it. And I think we once saw it because we once disassembled a program and there was a reference to a data section and there was a segment essentially. It was something, the address looked something like DS0, which means that it's a zero address at the very beginning of the data section, right? Okay, so the CPU just assumes that you by default you use those segments, and if you really want to override, you occasionally generate an instruction which uses explicit value of a segment, right? That's why you never seen them, right? So essentially, instead of like seeing instructions like that, you just essentially never see those, right? But that's fine. That's how it works, essentially. So like same idea which I was trying to explain, infer the code data and stack segments from the instruction type, right? So not a big deal. Code segment, data segment, stack segment. Okay, now coming back to the problems. So let's step back for a second and ask a question. So what did we achieve with segmentation, right? So we started by saying we want to provide the illusion of a private address space to each program, right? And it does provide it. So we can implement fork, right? So remember fork. So what does the fork, what does it do? Fork would be a little bit hard with my software fork isolation model, all possible, right? So what fork will do is you say, look, I was running on this segment. It was pointing here. This is my address space. You do a fork and you say, look, I will essentially, if this was physical memory, I would copy this physical memory somewhere else as well, right? So this was, for example, parent. Oh, sorry. Yeah. I'm creating a child. The child will be running here. And for the child, we will set a base to point here. They are absolutely identical, right? So all the data sections, all the stack, everything is identical. And I just, since fork returns a PID, right? So what does it mean? What's this difference? One is a parent ID, another is 0. What part of your execution environment will be different? Just this one part between parent and child. How do we return PID? It was just yesterday for you guys. Where, like, is it in memory? I claim that I can just copy the memory and it will run. I'll just change one thing for the fork. So what is this thing? RAX, right? So this, remember, the calling convention tells us that we return addresses in the EAX or AX or RAX, depending on the size of your architecture. Right, so literally just this one register will be 0 for the child and will contain PID for the parent. But that's how the operating system can build fork, right? Okay, so someone was saying, okay, we don't have isolation or protection between processes, right? So I claim that we achieve that as well. So through what mechanism? So if you have an address which has a move instruction here, which tries to access something outside of a segment, then what happens? Yeah, this is exactly like the hardware will, the hardware will look up through the table, global descriptor table, for example. We'll pick the base, we'll pick the limit, we'll check that the limit is greater than the address. And this is the word which you know, this is the seg fault, so segmentation fault. Essentially, you're trying to access memory out of bounds, right? Agree with this? So no matter which address you make up here in your program, you cannot access anything outside of this segment because of the limit, right? Agree? Okay, so at least we learned what segmentation fault is, right? So, or how it historically got its name, likely, right? So it just got it from this scheme where segmentation enforces the limits. So far so good. So segmentation is not bad, and people were running it for quite a while, right? Because it has it only minorly changes the organization of your CPU, right? So because you can imagine that, the logic to implement these checks are minimal, a couple of LEUs to do addition, subtraction, comparisons, right? But can be done in parallel with other operations in a pipeline. So, but relatively simple. But let's talk about problems. So what can go wrong, or why it's not ideal? It's a nice mechanism, can work in embedded operating system, for example. Be it a software fault isolation segment enforced in software, or the segmentation in hardware. Okay, what problems are you going to start running into with segmentation?
It doesn't distinguish between code and data, so it's not going to protect you from modifying your code.
It actually does. I mean, I'm sorry that I didn't make it explicit. When we start running operating systems like our wonderful x86, you will immediately crash if you don't distinguish between code and data. Remember, there is when you have a jump instruction, for example, control flow, the CPU infers that you're going through CS segment. CS segment can have this, for example, and for example, data will start from here. So it's very well distinguishes, and it even protects the stack. That's actually a beauty of this model, that actually doesn't allow you, you can protect the code and data, right? And you can actually, remember I was saying access flags, you can configure a data segment and you can configure a couple of them. You can say 1 and 2, and 1, for example, will be read-only access to here, and this will be a read-write access to here. And then you can, it depends on how strict your enforcement is in the program, in the code. Because typically when you say, okay, you will have to switch between them. So you have to think carefully about how it can work. So that actually works. And I appreciate the question because it clarifies for everyone what's going on here, right? What else? But okay, this seems to be okay. Yeah, but maybe it's.
What if you run out of memory in your segment?
Right, exactly. So this is what I have on my slides as well. You say, I want more memory because I somehow didn't guess the limit of the segment up front. And clearly you say like if it has to be continuous, right? Because that's how the semantics of malloc. It doesn't like it returns you pointers, right? But and you can run with disjoint address spaces, but it gets painful. So you need like funky compiler support. But people were doing it, like 8086, everything was disjoint. Just move between those segments, but it's pain, right? And so here the problem is that you're running into some other segment. And at this point, you have a couple of options. You say, look, maybe I will just move that other segment. So you just copy the memory by some number of, by some offset, and maybe patch this base. So kind of like works, but copy is expensive, like especially if you're talking like gigabytes. You know, like to copy a gigabyte, you probably need like, I don't know, maybe you can copy something like 20 bytes per cycle. I don't know, depending on how clever you are, maybe even 5, maybe like 64 bytes per cycle, maybe even more. But copy is actually reasonably fast, but still like it's a lot of cycles. Gigabyte is billions, right? So it's in billions of cycles, right? Or in hundreds of tens of millions of cycles. So it's like milliseconds. So it's like human sees that, like feels when we talk about milliseconds, the human can perceive this this time, right, and feel it. So it's not super ideal. You can even like move it to disk, something like, remember we talked about swap in and swap out. You can say I can take the whole segment to disk. But again, the same problem. It's a binary thing. You either take all of it or none, right? And it takes a while to move this thing to disk, just because disks are even slower than copying memory. Because memory is like, again, thousands times or millions times faster than disks, right? So not ideal. So you end up with this problems that you have to move the entire segment. The address space gets fragmented, right? So there are gaps, and you kind of still have free space because you didn't use the whole physical memory, but still, you cannot use it in any meaningful way because you have to like move everything around to just, get a larger chunk, right? And this is where the idea of paging comes in. So who can tell me what paging is about? So how does it improve our segmentation? What's the core insight? Right. So let me repeat what you say, because I can hear you. I don't know what you're saying. So the main idea is to, instead of having those large segments, let's just split memory into small chunks, which are called pages. So pages can be of different size on modern hardware, but like the canonical size is 4096 bytes or 4 kilobytes, right? And essentially translate from the addresses in that page, in each page, into physical addresses. They don't have to be continuous. This can be mapped here, for example. This can go here. This can go here, right? So virtual address, which sits inside the page, we will use some data structure, which essentially takes the, you say, virtual and translates it into physical, right? And this is what we will do next time. So next time we'll cover paging, and we'll be done with address translation. Okay, so thank you. If there are any questions, go for it. If not, we're done. All good? Everyone is happy, okay. Yeah. I'm sure you will enjoy it while doing homeworks later.